So it's my pleasure to introduce Anna Frischman from Technion in Israel. And so Anna has a BSc in physics and maths from Tel Aviv, and then did an MSc in high energy physics. And as many of us, she then saw the light and switched to something else, and did a PhD in the area of turbulence in 2016 at the Weizmann Institute. And she was then a postdoc in Princeton and is now on the faculty of Technion in the physics department. And the topic for today is learning force fields from stochastic trajectories. So the screen is yours, Anna.
Thank you very much. And thank you very much for the kind invitation. So actually, since I've been back in Israel, I've been working more on turbulence stuff. But today I'll tell you about something that we've started with Pierre Onseret when we were both postdocs at Princeton at PCTS. I thought it might be more fitting for this audience. Yeah, so you can see Pierre here, and this talk is based on our publication from 2020. Okay, and Pierre is now in Marseille. Okay, so the basic question of this talk is, given some sampling of a phase-space trajectory of a dynamical system, some kind of dynamical system that we don't know much about, can we infer the underlying dynamics? And of course, this question is very broad. So one thing you can observe here is that there's evidently, it's not a deterministic trajectory, but there is some kind of noise. And what, when you think, for example, about biological systems or soft matter systems or complex systems, there are various sources of noise you could have. So one type of noise is something we know from physics, from very standard textbooks, is thermal noise. So Brownian agitation, like if you put a colloid in a solution, you would see it jiggle. It's not because it's alive, it's because there's thermal noise. There are fluid molecules that bump into it. And the same thing would happen to any small object that you put in there, for example, like a virus. Another type of noise you could have is noise from active processes. So for example, if you're thinking about a protein that's moving on a cell membrane, then already you have some processes which break time reversal symmetry. The same for cilium. There are these protrusions, these hairs protruding from cells. So they move and they fluctuate, and most likely it's really because of active processes. And then there is also a type of noise that you could call from complexity, even though you could call all of these also in some sense as noise from complexity. And that has to do with the fact that, well, a system could have many degrees of freedom, and only some of them are accessible to us, or some of them are slow. And so we observe the other degrees of freedom as some effective noise. So this is, for example, a trajectory of climate oscillations with some phase space of temperature and surface ocean height, or you can think about a cell moving. Right. Now, apart from the noise, of course, there is also a deterministic part to the dynamics, and that deterministic part is the thing that shapes the trajectory, and it competes with the noise. So, right, so there's this looks like just Brownian motion, whereas here evidently there is some underlying deterministic force. And the basic question that we'd like to ask is, how do we learn these forces? Okay, so still this was too broad because there are various types of dynamical systems you can think about. But here I'm just going to focus on one class of systems, which is basically the simplest model you can think about, which is Brownian Dynamics. So it's a first order differential equation, stochastic differential equation. So what I call the force is this F here. Okay, so it's a dynamical equation, x dot is dx dt. And then I have the diffusion coefficient, and this is the white noise, right, white in time noise. And this is a generic model for dynamical systems which have fast unresolved degrees of freedom, right? So if they are fast, then we can't resolve them, they'll just throw them into the noise. And because they are fast, we can assume that the noise is, apart from being white, also is Gaussian. So that's the standard thing. And this is why this is sort of generic. And of course, in the physics context, we are familiar with this in the context of an overdamped Langevin equation, right? So if we have a particle that is small enough, then it has a small Reynolds number. So this means that it has vanishing inertia. So basically what's written here is a force balance, but it doesn't have an acceleration. Instead, it has a velocity which is proportional to the force, and that has to do with Stokes drag, right? And m is the mobility matrix in this case. And this is what but even though actually the physical force is the mobility times the force, I will refer to this big F as what I want to infer as the drift or the kinematic force. And then, of course, there is also the noise part, which has to do with the fact that the particles inside a bath or a solution, and there are, fluid particles that hit at it at random. So you get this sort of fluctuating force, but that fluctuating force is not unrelated to, the dissipative processes. If this is a system in thermal equilibrium, if this is really a thermal bath, in that case, there is a relation between the diffusion coefficient and the mobility matrix, which are related through the temperature. But of course, if the system is something which has an active noise in it and the degrees of freedom that we throw in here are active, then this relation, of course, does not have to hold anymore. Okay. Okay, so what is the problem that I want to address? It's this inverse problem. So let's say that I'm given a d-dimensional trajectory of positions, orientations, etc. So some experimental trajectory is a function of time. Okay. What I want to learn is I assume that it satisfies Brownian dynamics, and I want to learn the force, and I also maybe want to learn the diffusion. And in general, these are fields, okay, which I want to learn. Okay. So one thing you could ask is like, why is it interesting to consider this inverse problem? So you could have a few answers. So one thing you could say is that you're interested in studying interactions, maybe interactions between colloidal particles, or maybe interactions between bacteria or active cells. Another thing you would like is maybe in the context of complex systems like the climate. Maybe you want to, infer a minimal model and have something predictive that you could use. And another perspective is that maybe you have optical tweezers and you want to calibrate your instrument and see that the force you're applying is what what you think it is. And then there's also this sort of more recent motivation where maybe you want to quantify the dissipation in the system, or how irreversible it is, or how far from equilibrium it is. And this is also something that's been of interest lately, I think, a lot. And so in other words, what you might want to say is that you want to infer the entropy production rate. And in this case, the entropy, so let's again imagine that we do have a thermal bath. In this case, the entropy is given by the heat produced in the bath divided by the temperature. Now, since it's an overdamped system, the heat that's produced in the bath is the same as the work that's done by the force. So that's x dot f dt. But you can also write it in a different way, which is using the relation between the mobility matrix and the diffusion coefficient, which is given by this 1/t. I can write it in this form. And so it means that if I infer the drift and I know the diffusion coefficient, then I can also measure the entropy production. Okay. Okay, so I've been talking about inference of forces and inference of the diffusion coefficient. And so the question is, what is easy and what is hard to do? Okay, so one naive thing we could say is like, okay, so this is the, SDE, the stochastic differential equation, and let's discretize it, right? So we know that the noise goes like square root of delta t, right? This is something that if you solve an equation on the computer, you have to use for white noise in time. And then let's just, try and construct an estimator for the diffusion coefficient. So what we could do, this is basically Kramer-Royal. You take delta x squared, you divide it by delta t, you get the diffusion coefficient, and then you have some order 1 correction. You could also try and construct such an estimator for the force, but then in this case, you have a term that goes like delta t to the -1/2. So that is telling you that this is, in some sense, a low noise problem, where this is a high noise problem, right? As you go to smaller and smaller delta t, this term is basically swamped by the Brownian noise. So in a sense, there is some information limitation, or we have to have long enough trajectories if we want to be able to infer the force, right? And you can also think about it as a transition between a diffusive to a persistent regime. By the way, if you have any questions, please feel free to ask and to jump in. Okay. So what we will do is we will focus on the force inference, because the diffusion, basically, more or less, you can use this sort of estimator. But I will also specify some things about it. Okay, so what I'm going to talk about, or the way I'm going to present the topic in this talk, is that first I'm going to give some kind of somewhat abstract connections between force inference and communication theory, and also some connections to stochastic thermodynamics, or sort of related to the entropy production and things like this. And then in the second part, I'm going to introduce a practical method for inference of forces and of currents. And the relation between the two parts, it's not going to be very rigorous, but there's going to be some inspiration from the first part for the inference in the second part. Okay, so the setup, as I had said before, it's Brownian dynamics, and I'm going to infer this F, and I'm going to assume for this part that the diffusion coefficient is constant. Of course, you also can consider a multiplicative noise, that things become more, a bit more complicated. You then have to define the drift and say exactly what convention you're using. So I'm just going to avoid it in this part. Okay. So why do I talk about communication theory? Because one way to think about the inference problem is the basic question: is there enough information about the force field in the trajectory? And we saw that if the trajectory is very short, then all that we see is just a diffusion, right? It swamps all the information about the force. So we want to sort of quantify it in some way. And I think sort of a nice way to think about it is in a sense that the trajectory is like a noisy transmission channel for the force field. Okay, so what is a communication channel or a transmission channel? It's something where you take a signal, you put it through the channel, and then it comes out like not the signal that you put in, but the signal plus noise. So in this sense, I want to make this analogy between the trajectory that we want to read the force from and this communication channel. So to make it more specific, so again, the framework of a transmission channel, it's been known since and used in our everyday life, but not so much by physicists. So the idea is that I have a bunch of messages that I want to transmit. And so then I need to decide on some sophisticated encoding scheme, right? So I put in a message and I get out a code word, and that code word goes through the channel. Now, unfortunately, the channel has some noise in it, so it comes out as the code word plus noise, and then it goes through a decoder. So I have some algorithm here that allows me to read that code word and make very small errors, right? That's the goal, and to estimate this message. So what is the analogy here? So the message here is my force field, right? So I want to learn what is this force field that's underlying the dynamics. My encoder, so here I don't have any control of the encoder. The encoder is just the dynamics, right? The dynamics of the trajectory that I'm observing. And so the code word is just a sampling of the force at various instants of time. Okay, but then it goes through the channel, and the thing that I actually can read out, I cannot read out directly this code word. Instead, what I can read out is this x dot, which also has the noise in it. And then my goal is similar to this estimate of message, is to infer FPU. So this is sort of the analogy. Okay, and then, okay, if you're talking about a transmission channel, then you need to specify some things. So for example, this is a continuous time channel, and it's a Gaussian channel. So why is it Gaussian? Because the noise is Gaussian, okay? Okay, and so now we can try and sort of use the tools of transmission theory or information theory to answer this question of, is there enough information about the force field in the trajectory? Right? And for this, we can use the notion of a channel capacity. So the channel capacity is the maximum rate with which information can be transmitted through the channel. And it can also be said in a different way. So as my message, or as my trajectory increasingly becomes longer and longer, there is a larger number of distinguishable signals. And the maximum number of distinguishable signals, it grows exponentially. And the exponent with which it grows with time is the channel capacity. And there is a formula for it, right? But this channel capacity, it puts a fundamental bound on the rate with which we can infer the force. Okay, so now I want to sort of use the formula from communication theory. So I want to phrase things in the way that things are phrased in this sort of communication theory works. So let me write, so what I'm measuring is this delta x delta t, and I'm assuming I have a finite sampling rate, right? Because that's what I have in practice. And I'm just rewriting the noise in this way, and then I'm writing the variance of the noise in this way, just dividing by delta t. Okay, so when you have a signal that you're trying to transmit through a channel, then if you wouldn't, so this is, right, this is not about the trajectory right now, it's just about transmission of communication. So if you didn't have any limitation on the power of the signal that you're considering, you could actually have an infinite capacity, okay? So your channel capacity is unlimited. But of course, in practice, you always have some power with which you can transmit. So this is this power constraint, right? So you're considering all the signals or all the code words you could transmit, which have this power constraint. And then you also need to say something about the variance of the noise, right? It's assumed to be average 0, but it has some variance. And in this case, it's this 2d over delta t, right? And n is the number of samples that we're using. Okay, so there is a famous formula, which is called the Shannon-Hartley formula for the channel capacity. And it reads the following, it's 1 over, so this is for a finite sampling rate, so that's why there is a 1 over delta t. So it's 1/2 times 1 over delta t, log 2 of 1 plus p over n, right? Where p is the power of the signal, and n is the power of the noise. Now, okay, I'm not going to go into how this formula is derived. It basically comes from something very nice that's called the coding theorem, which says or proves that you can, in order to compute the channel capacity, so again, everything is in transmission theory, you could think about the mutual information between the input and the output, and the channel capacity is defined, or can be equivalently defined as the maximum mutual information between the two. And then you can show that the maximum mutual information is when you assume that the input is Gaussian, and this is how you get this formula. And then you can show that the channel capacity in the way that I had defined previously, where you have to define it a bit more carefully, which is the maximum rate with which you can transmit without error in some asymptotic notion, is equal to this. Okay, so this is sort of where it comes from. Okay. But now let's just use it for our case and just put in the, the variance and the power. And another thing we want to do is we want to take delta t to 0, right? And see what happens in that limit. So in this case, we have white noise, so the variance increases with delta t. On the other hand, we are sampling faster and faster. We might have expected that as we are sampling faster and faster, we have more information and it would diverge. But really it is finite, right? And this again has to do with the fact that at very small delta t, the noise is swamping the signal, right? So we get a finite number, this p over 4d. Okay, so in the context of the trajectory, what is the meaning of this power? So we can think about it as the average over time of f squared. Okay, and in the long time limit, it just converges to the average with respect to the steady state probability of the process of f squared, right, of our force. And so that means that this channel capacity, so it's a rate, right? It's some time scale. and you can write it as the average force, so the force squared average over 4 times the diffusion coefficient. Okay, so this is a finite number, and it's the maximum rate with which the information about the force field can be extracted from a continuous time infinite trajectory, right? So even if we take the limit of an infinite trajectory, continuous time, right, delta t going to 0, still this rate is finite. There is also an important point, and that is that in our case, where we are thinking about the encoding being just the dynamics, and what we are trying to read is this force. We don't control the encoding, right? In the case of the coding theorem, what's really nice is that you can really construct an algorithm so that you could decode in an optimal way. But here, of course, that's not the situation, and typically the rate with which the information is transmitted about the force is not really this rate, right? This is just a bound on it. But of course, if I have, yeah, okay.
Sorry?
Yes.
Yeah, I have a question with the calligraphic P that you define it. Like,
yes.
You first had like bounds on it, no? And then you bump it yes. into an equation. So it's like you are working now in bounds for the C, or this is real and
no, so it's the same. It's actually the same. So for any finite trajectory, it would be smaller or equal to P. Also for the case of our trajectories, but it's also fine to do it with the equality. Because you really prove it actually for a signal that satisfies the, right? It's a bound, so it's satisfied for the signal that satisfies the bound, the equality.
Okay, so it's not a bound, is real inequality. Okay, thank you.
Yeah, no, but it is a bound in the sense that, I mean, here it's really an equality, but it's a bound in the sense that the rate with which the information is transmitted is always smaller or equal to this. And in an actual channel, you can really, you can really construct an algorithm where you can come arbitrarily close to this rate. But in our system, then, there's no reason why the dynamics would be optimal in this way. And it, usually it won't be.
Thank you.
Thanks for the question. Okay. Okay, so now I want to talk a bit about, okay, so there is this channel capacity and there is information in the trajectory about the force. And now I want to talk a bit about what kind of information there is in the trajectory, okay? And for this, I'm going to use the Fokker-Planck equation. Okay? So it's just, instead of using the formulation of the Langevin equation, I can talk about probabilities and probability currents. And there is this continuity equation for the probability density function. And the probability current is given by this formula, right? So it's the force times P of x minus d mu nu P of x. By the way, I'm using the Einstein convention, the summation convention, so I hope it's okay. I'm summing over this nu index here and also over this mu index. But if it's confusing you, just like imagine it's a 1D process. Okay, and I'm also going to assume that we are in a statistical steady state because we're kind of considering these very long trajectories so that we can have statistics. Okay, so in this case, okay, in the steady state, then our probability density does not depend on time. There is a unique solution, and okay, it satisfies that the divergence of J is equal to 0. But if we are in equilibrium, then we also know that the current is 0, right? Time reversal symmetry is conserved. There is no preferred direction. X here is an even coordinate. So that means there should be no current to any direction. So the current should be 0. And then in that case, we can, equate this to 0. And here I did some manipulation because we're assuming we're in equilibrium. Then we can also use this relation between the diffusion metrics and the mobility metrics and write it this way. And this is nothing else but just, saying that this is a Boltzmann factor, right? If I write the force, this means that I can write the force as a gradient of something, and it's a gradient of the potential, and then I get this Boltzmann factor, right? I didn't normalize it, but it should be proportional to, right? But what it shows us is that if we are in equilibrium, then all the information we need to know is already there in the steady state PDF, right? So actually we don't need to know any time ordering or anything like that. All the information is already there from, steady state PDF. And this is, this is something, of course, people know, and it has been used for force inference when you have an equilibrium system. Okay. But of course, it's not so trivial. You would actually want to have an estimator for the log of P, because, measuring P is, it might be non-trivial to measure the log of P. Okay. But in general, you don't have current that vanishes. So then let's express the force in terms of the current and this other piece, right? So before we only had this other piece, and now we have this J mu over P. And we can think about it as an average phase space velocity, right? Like always the current is, the velocity is the current divided by the density, right? In phase space. So this is something like a velocity, and it breaks time reversal symmetry, right? Of course, it means that there is some preferred direction at a particular point in space where, my particle, let's say it's a particle, tries to go in, okay, some particular direction, and that means that time reversal symmetry is broken. Okay, so in general, the force has both components that have to do with time reversal symmetry breaking and components that have to do with just the structure of the steady state PDF. Okay, so now this is the part where I want to sort of connect the stuff about the channel capacity with some stochastic thermodynamics, and it directly relates to what I've been talking about just a second ago. Sorry, maybe yeah. Okay, sorry. So what I want to say is that actually you can write the channel capacity as a sum of two positive terms, one of which is the entropy production rate. Okay, so let me have like another slide about the entropy production rate. So you can write it in two ways, really. So one way is actually this last one that I talked about before, which is this heat produced or work divided by the temperature, which you can also write in this way as Fd minus 1V, as we talked before. But you could also actually show that in the steady state, this is equivalent, or there are some boundary terms that go to 0, and you can also write it as this positive definite term, which is Vd minus 1V. And these are equivalent formulations in the steady state. So what I'm saying, and that's sort of using this relation that I just talked a minute before, is that the channel capacity, which is Fd minus 1F average, can be written as Vd minus 1V average plus some term which is also positive definite, and actually the sort of cross term here vanishes. Okay, so I'm not going to say too much about this term. So people have discovered it before. They called it the inflow rate, for example, in this paper. And it has to do really with this, the derivative of the log of the probability density function. You can think about it as some structural term that tells you something about the directions in phase space that do not have to do with currents, but maybe like have to do with a minima. And so from this perspective, from the fact that the force, you can write it in this way that has to do with time reversal symmetry breaking, and another part which has to do with just the structure of the phase space or the structure of the probability in the phase space, you can write the information as a sum of the entropy production rate, which is dissipative and tells you sort of go there, and something that has to do with the spatial structure, which in a sense says stay here. Okay, and I think it's a sort of both a nice point and maybe an important point to remember when you use inference. Okay, and this sort of relation will return in some way in the inference scheme. Okay, and I want to sort of introduce yet another way of thinking about this channel capacity, which is maybe more intuitive for physicists. So, and define something on the trajectory level, right? So let's say I have a sampling of the positions of the, of my system at various times with some right? And I will denote this probability of having the trajectory given a particular force by this P. Okay, and I'm going to use the notion or the definition of a Kubler-Kleibler divergence, which is something like a distance between probabilities. It's not really a distance because it's not symmetric, but basically, I think there should be a minus here. Basically, when the two probabilities are the same, you get 0. So in this sense, it sort of measures the distance between the two probabilities. And what you can show is that the same channel capacity that I defined before, you can also get it by using the path integral formula for these probabilities by looking at the Kubler-Kleibler divergence rate. So here you see that I'm dividing by the time and taking the time to infinity. So I'm taking longer and longer trajectories. And what I'm doing is I'm comparing a trajectory which has a force with a trajectory which has no force. So in a sense, what it's doing, it's showing me the rate at which trajectories become distinguishable from pure Brownian motion, right? So that's the rate with which I can learn something about the force. Okay. Okay, so now we can go back to the inference problem. So what we've learned is that there is a finite capacity for a trajectory of length tau, okay? And meaning there is a finite information. And on the other hand, the force field in principle has an infinite number of degrees of freedom to infer. So this means that obviously we need to fit, right? We can't, we cannot fit to all the infinite degrees of freedom. Okay, so we need to approximate the force field. And again, one naive or one kind of simple way to do this is to go back to this instantaneous force estimator that I presented before. And if you do maximum likelihood and assuming that you bin stuff, right? So you coarse grain space and you create these bins and you average within a particular bin, then you have some estimator for the force. And this is something that people have used before. It's been, I think, frequently used. I'm showing these two examples from sort of biological examples, but I think there are many more. But the problem is that it doesn't really represent well the force field, because usually we think of the force field as being something smooth rather than really, this choppy thing. So that seems not very efficient to divide it into these squares. And it's also not very efficient in terms of the data, right? There's not many, you need a lot of information in each one of these bins. And it's also, right, it's a lot of, you divide the space into a lot of bins. That means that your number of degrees of freedom you need to fit grows exponentially, and that doesn't generalize very well to high dimensions. So what we'd like to do is to do something that's, that's a bit better. Okay, so the idea here would be to do a least squares fit, so nothing too fancy, but taking with smooth, so this should be state-dependent functions, okay? And this is, so we did not know that at the time, but this is actually not a new idea. So people have thought about it. So in this paper, they, discussed this in one-dimensional process, and in this paper, which is more recent, they've done this using some sparsity conditions. I will mention what are the differences in what Pierre and I have proposed. And and I think there are probably many works that have sort of similar ideas. Okay, so what we want to do is we want to estimate the force from the trajectory, right? So we have a sampling of the trajectory, and here I have some time samples that are, delta t apart. So what we'll do is we'll choose a basis of functions, right? Could be polynomials, could be Fourier, could be whatever you want, right? But you do need to choose a basis of functions, right? The method doesn't give you. And then what you do is you do least squares, right? So you minimize. So you take that local estimator, that delta x, and you minimize the distance to something which is a combination, a linear combination of these basis functions that you chose. And then you have an approximation of your force as a linear combination of these basis functions. And you can solve this least squares fit. And it also turns out to be the maximum log likelihood for the system. And what you can do, so you basically, this is the solution to this least square problem. And there is this b to the -1/2 matrix that appears here, which is basically has to do with the normalization of these basis functions that you chose, with respect to the empirical measure. So in a sense, what you can do is instead of these b minus 1/2 b alpha factor that I wrote here, you can think about this as some, I'm just calling it a C here. And these C's are like projectors. And you can think about them as projectors with respect to the empirical measure, right? So the empirical measure is basically, I can replace this time integral by some space integral by inserting, some empirical measure here. This is what I call an empirical measure. And when the time goes to infinity, this empirical measure would, if the system is in steady state, would go to the, probability density, the stationary probability density of the system. Okay, so they basically serve as projectors. They project this x dot onto this basis with respect to the empirical measure. Okay, that's the dot product that we're using. That's another way to think about this least squares fit. Okay, and so if we can think about it in this way, then we remember that the channel capacity is basically also like is a bilinear function of the force with, again, with this measure of the probability density. And so the capacity of the projected force field, right, which has now a finite number of degrees of freedom, also takes this sort of form, right, of f d minus 1. And of course, it's only part of the full channel capacity. But now we have a finite number of degrees of freedom to infer, right? So then we have the hope that we can really infer them. Okay, so we are approximating our force by these finite number of basis functions, and we can think about it as a projection of the original force onto this basis with respect to this measure. Okay. And the other nice thing is that you can, in the long time limit, you can get a self-consistent estimate for the relative error. Okay, so this is just what's written here. It's the relative error. The f hat is the estimator that we've suggested, and then this is normalized by the estimate itself. So the relative error goes like the number of degrees of freedom. Okay, so it's the number of space dimensions times the number of basis functions divided by twice what we call in this context something like an information in the trajectory, right? So it's the inferred channel capacity times the time, right? So it's the amount of information that we are inferring that exists in the trajectory, okay? So it means, again, this is sort of roughly where the first part connects, is that the inference becomes possible if the information in the trajectory that we infer is larger than the number of degrees of freedom. Okay, so we have, at least a bit of information per degree of freedom. Okay, but the estimator that I suggested is, a time difference. It's a derivative, and if we are thinking about, so in some situations we don't need to worry about measurement noise, like maybe we were trying to model something complicated that we have numerical simulations of. But if we're thinking in the soft matter or biological matter context, then there's usually measurement noise. And taking these sorts of derivatives is, usually is very bad. It's a very bad idea. So what we want to do is we want to change this estimator so that it will be robust to this measurement noise. And that's sort of the basic novel ingredient that Pierre and I really introduced. So we weren't aware of the previous works, but I think this is the really novel ingredient. Okay, so what we do is we recall that we can also write the force as the velocity times something that has to do with the steady state probability density. Okay, and we can build an estimator for the velocity. And basically the difference between the velocity, what I call the velocity, and the drift is basically Ito versus Stratonovich convention. Okay, so here when I'm taking the time derivative, I'm evaluating my basis functions at a point in the middle between the two. Whereas if I was, measuring the drift, then I would have been evaluating it at a point which is the, x of t of I, right, in the past. Okay. So when I use this convention, so why is it, so first of all, this gives me the velocity, but why is this beneficial in terms of measurement noise? Yeah, so the reason is that I don't know if you can see it from here, but if you expand this term, you can see that you have telescopic, it's a telescopic sum. So the noise terms just cancel out. And in a sense, it also has to do with the time reversal properties of this velocity. And assuming, of course, that the measurement noise is uncorrelated in time. Okay. So the advantage is now that when we use this sort of derivative, that when we measure the velocity, then it's unbiased by measurement noise. And then this part is really something analogous to this d nu log p. It's just that we sort of did an integration by parts. So now we get a derivative of our basis functions or of our projectors. And that means that, well, this part does not require time ordering, but it does require a smooth basis. So for example, if you want to bin things, then you wouldn't be able to use this method, right? Okay. And then there is another point. So far I've been sort of ignoring the fact that maybe we don't know the diffusion coefficient in advance. And here we actually, what we can do is, because this formula does rely on the diffusion coefficient, is that we can put here a local estimator of the diffusion coefficient. You could also put something that's, again, you would hear the estimator that I wrote has some issues with measurement noise, but you can correct the bias due to measurement noise and make it unbiased. Okay. So another bonus from having an estimator for the velocity is that we can also have some estimate of the entropy production. Right? And very similarly to the channel capacity, you can again think that you are projecting onto this basis and you have some entropy production. So in a sense, you can think about it as you have the information, you choose the basis, and the basis is sort of like dividing the information that you have into a sub-channel, and that sub-channel has its own entropy production and its own channel capacity, and it's going to be positive, but smaller than the total entropy production rate. So it would give you a lower bound on the total entropy production rate. Okay. So to summarize the method of stochastic force inference that I presented, you choose a projection basis and construct these projectors, okay? And then you compute the projected force from this formula, and then you can sort of iterate by looking at the relative squared error and seeing that this is small, right? So maybe you want to increase the number of polynomials in your basis until you have, but it's making sure you have sufficient information to resolve things. And you don't need to implement this method by yourself because Pierre has everything, both the manual of how to use the method and also the code on his GitHub page. Okay. So let me show you some data from simulations, from simulated data. So the first thing you could do is sort of the easiest thing. You have an Ornstein-Uhlenbeck process, so a harmonic potential in 2D, a linear force. Right. And then you could, apply SFI, and you can measure here the inference error and here our estimate, and you can see that they agree very well. And this point is this point, and you can see that you can infer quite well the force. Okay, and maybe that's not surprising because we chose, in a sense, an adapted basis, right? We knew from the start what kind of basis to choose to represent this. Okay, so now we can use something more complicated. So here it's a sort of a Mexican hat with some rotation, so with some currents. And this we'd also like to use a polynomial basis. So here I'm kind of showing two things. So one thing is for this case, you see as you increase the order of the polynomial, you can capture more, but there is some saturation. And here, so you probably recognized it from my earlier slides. So this is the the Lorentz attractor with noise in this case. And here again, so really it's given by a second order polynomial. And what you see is that when I'm trying to introduce additional functions, then I'm actually having, I'm getting a worse fit, right? So there, of course, I can introduce more and more basis functions, but it could be that I'm starting to fit the noise instead of the signal, right? And for this, so one thing you could do, one thing you could ask is sort of, how does the information in the trajectory, how much do you get an increase in the information with the number of degrees of freedom? And here you also have an entropy. So you see there is some finite number of degrees of freedom that you need, and after which you basically kind of capture all of it. And you can also compare the sort of basis, the smooth basis, with just a grid coarse graining, which does worse, because basically it's spreading the information on coarser degrees of freedom, which are less relevant. Okay, and you can, okay, I mean, this is a detail about sort of how do you decide between, adding more functions to your basis. So initially, right, what you expect is that, so if you go back to here, initially you expect that you are capturing more and more information, but sort of when you are reaching here, then what's happening is that you're actually already starting to fit the noise, right? There isn't really more information or enough information in the trajectory. So, and you can estimate it. So we have a sort of an overfitting criterion, which has to do with the variance of the information that you're getting. And this has to do with these stars here, which you can estimate. Okay. And then maybe I guess the almost last thing I'm going to talk about is the diffusion coefficient inference. So what happens when the diffusion coefficient is phase dependent, before I assume that it was constant? So you can do a very similar scheme. So again, you can replace it by some unbiased estimator, but again, you use this idea of these projections. And this has already been used in a recent paper on, looking at a charged particle near a wall. And in this case, you have space-dependent mobility and therefore also space-dependent diffusion. And there is some theoretical expectation, I think. And then I think it's actually, I'm not sure. No, I guess these are the fits and these are the points from the experiment. Okay, so they already kind of used our method to infer this. Okay, and you could also ask about force inference. In this case of multiplicative noise, it becomes a bit more delicate. So our previous estimator, it works for the drift. So if you write this in Ito, and there is an additional term. So this would be the kinematic force, or what I called the force before. But in order to infer it from the drift, you would have to have an estimate for the divergence of the diffusion coefficient, and that's sort of non-trivial, at least in our sort of scheme. And then the final thing you could ask is also what happens, I've talked about these colloidal systems where you have a lot of particles. And you can ask, well, what do you do in this case? So for example, here, I think Pierre simulated these self-propelled particles, which have also soft repulsive interactions. And maybe you want to infer the interactions between them. And you might think that this is a high dimensional phase space, right? Each particle has its own phase space. And maybe there's not enough information per degree of freedom to infer things. But in this case, what you could use is you could use the fact that these particles are indistinguishable, right? And have some sort of expansion where you consider the average force they feel, then you consider pairs, and you can average over all the pairs, and then three-body interactions, etc. So you can use this sort of expansion in the basis. And this is what Pierre had done. And you can see that here, I think there's like 100 frames or something like that, and already you can infer quite well. So you choose this. You have the orientation, and you choose a basis for the orientation, and you have the sort of the interactions, and you choose the basis for that. Yeah. Okay. So I think with this, I'm done. And I want to summarize to say that I showed you a link between communication theory and Brownian dynamics using the idea of the channel capacity. And then I showed you a practical method to infer forces and currents and the bound on the entropy production. So our original work we published in 2020, and then Pierre and his collaborators sort of expanded or used this method. So they expanded it to underdamped systems where you have inertia, and they used it for example, for motility of cells. And they've also used it, I think, the method for inference from sort of movies. Okay, so with this, I thank you for your attention.
Okay, thank you. So this is open for discussion or questions. If anybody has any, just unmute yourself and ask. I think.
Yes, I have one.
Go ahead. Yeah.
So yeah, you mentioned the case of the when you have multiplicative noise, but
Yes.
I didn't get like if in your method you have to like assume the kind of the shape of the noise, like if it is multiplicative or additive, like at the beginning of your process, or how does it work? Or you have something in the data that tells you how to proceed? Or...
Yeah, so what you could do, so here, I mean, for this estimator, you actually, it doesn't matter, right? If you just want to estimate the force, or this would be the drift, really, then you can use, you see, you don't assume, you don't, if you don't want to learn the diffusion coefficient, then you can just use this formula. What you would get in general is the drift. Okay, but then you can ask, okay, but is the diffusion coefficient space dependent or not? And you can try and fit it with, like our method doesn't tell you ahead of time. You could try and do sort of what I showed here, right? So you could try and do this sort of, and have in the basis something that's constant plus something that's, you know, that has some space dependence. And you can see if your relative error, right, is larger, like if there is enough information about this. And if there isn't, then you might as well assume that it's zero. And I should mention that sort of maybe this is something you would want to do using ideas of sparsity, right? So I think I briefly mentioned that in this paper. So they didn't use the same sort of inference with the correction for the measurement noise, but they did discuss, you know, you can add to the least squares fit, you can add a condition, like an L1 conditions that makes it sparse, right? So that you don't, you know, if you get coefficients that are very small, you just put them to zero. So in a sense, maybe this is one thing you could do, or you could look at the relative error and see if it's significant or not.
Okay, but it's like a second step, like you always start with the drift and then you jump into asking questions about usually, the noise.
Yeah, I think usually you would, this is what you would do. I think also, like, you know, usually you sort of have some idea. And I guess what you would initially assume is that the drift is, that the diffusion is constant. I think this is what you would assume initially. And then if you see that things are inconsistent, then you would change that.
Okay, thank you very much.
Thank you for the question.
Anybody else? Any comments or questions, thoughts?
Yeah, and of course there are many many people that have been thinking about kind of different methods. Some have like Bayesian methods and using neural networks. And I think some of the methods have really focused on cases where you have gaps in your data. So you don't have recordings in some of the, so for example, for climate modeling, maybe you would have such a time series, and our method doesn't, I mean, it might work for these cases, but it's not constructed for these sort of cases. It's more for kind of, you know, soft and bio sort of cases where you really can do an experiment and you can measure things. And of course, if you have gaps, then you might not be able to measure the currents. Yeah, so that's another thing I wanted to say.
So would this work? So this is all sort of based on stochastic differential equations, right? So
yes.
What if you have a discrete space and some kind of chemical reaction system or population or something? Is that?
So I think, so I'd have to think about it more carefully. My intuition says that it's a different class sort of systems, and you'd want to use maybe a different method. But yeah, but I'm not sure, because here really you sort of have sort of a clear distinction between
Yes.
the noise and the deterministic part.
Yeah. Yeah. Mm.
Yes, I think. I mean, what another thing we're thinking about now is sort of more seriously about is to use these ideas of the information in the trajectory in what happens if you have hidden degrees of freedom. So if you have hidden degrees of freedom, you don't observe some of your degrees of freedom, which are, you don't observe them, but they're also not fast. You can throw them into the white noise. Then can you learn anything about those? You can certainly do you can certainly average over those degrees of freedom and use our method. But the question is, can you learn something about those degrees of freedom? And we are thinking that maybe somehow you can distinguish between regimes where you can and you cannot, using this idea of the information in the trajectory, and how much bits do you have about, you know, the hidden degrees of freedom. Yeah.
Anybody else? Any questions or no? Doesn't seem to be the case. Well, then thank you again.
Thank you very much
for your talk. And now the only thing I can do is press the button to close the thing. I can't do anything else. So okay. Thank you.
Thank you.
Bye-bye.
Bye. Thank you for listening.
Bye.